Okay, so let's get into graphing the trig functions. First and foremost, we're going to start graphing cosine and sine. Now here's the deal. Remember when we were graphing the parabola? We graphed y equals x squared. And when we knew what that parent graph looked like, depending on where the numbers were placed, and if they were added or subtracted or even multiplied, told us if the x's were affected, which means the parabola shifted left and right, or if the y's were affected, which means it moved up and down. Same scenario here. I need to know what the parent graphs of cosine and sine look like. So when they start tacking on numbers, either adding or subtracting or multiplying them, then it's either going to affect the x's, which is left and right, or the y's, which is up and down. Now, one of the things I need you to understand is this. When we graph cosine and sine functions, we are basically unwrapping this unit circle. Okay? We are unwrapping it based upon the cosine function or the sine function. So I've drawn this here to remind us that, and I have it in radians, to remind us that of the points at each of these radian measurements. Remember, we start at 0 radians, pi over 2, pi, 3 pi over 2, and then back to 2 pi. And these are the points that go with each of them. Got it? Okay, so first function I want to graph is the cosine function. Now notice, I don't have any numbers added or subtracted to this cosine function. Nothing added or subtracted at the end, nothing added or subtracted to the x, nothing even in front. Well, in actuality, in front of cosine is a 1, isn't it? And in front of the x is also a 1, isn't it? 1 doesn't really change anything for us, as we already know. Good? Okay, so here's the deal. I am going to graph the cosine function in the positive direction of the angle measurements. I could also graph it in the negative direction, which won't make a difference because I'm going to get the same results either way. And if I go in the positive direction, 1 circle, 2 revolutions, 3 revolutions, I'm going to get the same pattern. Are y'all with me? Okay, so here's the deal. Let me get my grid system down here. And notice, there's 4 quadrants of the circle. I am going to have 4 intervals for this cosine graph. The circle starts at 0 radians. My graph is going to start at 0 radians. And then it goes to pi over 2 as the first major axis. And then it goes to pi. And then 3 pi over 2. And then at 2 pi. Are you with me? Okay. So now, I would like to graph the cosine function. And the first thing I'm going to find is the cosine of 0 radians. Remember, the cosine function deals with the x-coordinate. So in this case, at 0 radians, the x-coordinate is what? Yeah, the x-coordinate is 1. So when I take the cosine of 0 radians, I get 1. The next theta, the next angle I'm going to take the cosine of is pi over 2. So the cosine at pi over 2, remember, it's the x-coordinate. And the x-coordinate is, that's right, 0. The next angle I'm going to take the cosine of is pi. And remember, when I take the cosine of this angle, I'm looking at the x-coordinate, which is, that's right, -1. The next angle I'm looking at is 3 pi over 2. So when I take the cosine of 3 pi over 2, I'm looking at the x-coordinate, which is 0. And last but not least, I'm going to complete the circle and then back at 2 pi. And the cosine of 2 pi, I'm still looking at the x-coordinate, which is 1. So when I connect these dots, I end up with what I call the graph of a valley. Got it? It's the graph of a valley. Now, I could keep moving and take another revolution around the circle. But question is, will any of these x coordinates change? No, they won't. So in actuality, my graph will still continue and it'll still have the same shape, won't it? If I go backwards, if I go in the negative direction around the circle, my graph still isn't going to change because those values aren't going to change. With me? Okay, so here's a question for you. Now that we know what this graph or this unit circle looks like, when we unwrap it based on cosine, it's the shape of a valley, and it's going to keep being the valley all the way through if I keep going to the positive, more positive angle measurements, more rotations around the circle in the positive direction, or go on the rotation in the negative direction, I'm still going to get the same shapes. So here's a question for you. My question is this: what would be the domain of this cosine function? Hopefully you said, well, if it continues in both directions and it's the same shape, hopefully you said negative infinity to positive infinity. Does that make sense? The range. Okay, so what are the outputs? Well, if I look at the graph bottoms out at -1, doesn't it? And it tops out at +1. Agreed? And it's inclusive, which means it's going to be the brackets. Are you with me? Okay, so this is what the unit circle looks like when you graph it based on cosine. Cool? Okay, now let's switch gears. Now that we have cosine graphed, let's look at the sine graph. So you give me a few moments to erase and we'll be good. Does this make sense? Okay, to do these trig function graphs, you will always be using this unit circle. So you need to remember how to recreate it. Got it? You need to remember how to recreate this unit circle. So now I'm going to talk about the sine function. And I want to graph it based on the sine function. Again, the circle has 4 quadrants. That means I'm going to have 4 intervals to start with. Since there's nothing added or subtracted on here, I have no shifting going on. I'm going to start at 0 radians. And then I'm going to move to pi over 2. And then to pi. And then 3 pi over 2. And we're going to end back at 2 pi to complete that first rotation of the circle. Cool? Okay, so let's look. If I take the sine of 0 radians, remember, sine function is talking about the y-coordinate. So the sine at 0 radians is what? Yeah, it's 0. If I look at pi over 2 and I want the sine at pi over 2, sine function is the y-coordinate, and the y-coordinate at pi over 2 is, that's right, it's 1. If I now move to pi, and I'm talking about the sine of pi, sine function is the y-coordinate, which is, good, that's 0. If I move to 3 pi over 2 and look at the sine of 3 pi over 2, I'm looking at the y-coordinate, which is, good, -1. And I'm going to complete the circle and end back at 2 pi. And the sine at 2 pi is, excellent, it's 0 because it's the y-coordinate, isn't it? So if I take a look at my sine graph, I call this graph the graph of the mountain to the valley. Okay, that's the shape that I call it, from the mountain to the valley. Now, if I go another rotation in the positive direction, wouldn't this shape just repeat? Wouldn't I get the same shape again? And and so forth if I keep going in the positive direction? What about the negative direction? Yeah, it's going to be the same shape, isn't it? Right? It's going to be the same shape. It's not going to change just because we're moving in the negative direction. Cool? Okay, so let's look at the domain of the sine graph. What do you think the domain is? Yep, it's the exact same domain we had for the cosine graph. Negative infinity to positive infinity. It's the exact same domain. What do you think the range is? Yeah, bottoms out at -1, tops out at +1, exact same range. So the domain and range for cosine and sine are exactly the same. The graph shapes are different because the sine function is looking at the y coordinates, where the cosine function is looking at the x coordinates. Are you with me? Okay, so stay tuned. We're going to start tacking on numbers, and we got to figure out what it's going to do to these. Okay, so let's talk about one of the characteristics of graphing the sine and cosine function. It's known as the amplitude. And if you notice what I wrote down, there's now this letter a, this variable a, in front of the sine and the cosine functions. So first question I have for you is this. Is this a invading the space of x? Is this a attaching itself to the x, or is it attaching itself to the entire function? Good, it's attaching itself to the entire function, which means this. It means that this a, this amplitude, is affecting the y. It's affecting your y values. And if it's affecting your y values, that means it's going to affect your range. So understand that. That a that is now in front is not attaching itself to the x. It's attaching itself to the entire function, which means it's affecting the y values, which means it's also going to affect your range. So let me give you an example. Okay, now, when we graph trig functions, we should always graph them in the same order that we're learning these characteristics. Why? It's for the sake of consistency, okay? There's a reason why we go through these characteristics of graphing in the order we go through them. So when they give you a trig function to graph, the first thing you're going to ask yourself is, what's the amplitude? And in this case, your amplitude is going to be 3. By the way, major note to self, amplitude is always positive. Always. Because after you ask yourself the amplitude, there's one other question you should ask yourself with amplitude, but after you ask yourself about the amplitude, you should ask yourself if the graph is going to flip. And you're like, how do you know if it flips? Well, remember your parabola? How did you know if this parabola graph was going to flip? Yeah, there's a negative in front, right? Is there a negative in front of that 3? No. So will your graph flip? No, it won't. Okay, let's graph this, and you'll see one of the other items you should look at when you identify your amplitude. Now remember, your x's are not being affected. I'm still going to have 4 intervals. Since the x's are not affected, that means there's no left and right shift, which means I'm still going to start at 0 radians, and then pi over 2, and then pi, and then 3 pi over 2, and back to 2 pi. Right? Okay. My range was a +1, or I should say a -1 to a +1. Agreed? All right, so let's take a look at this one. 0. The cosine of 0 is what? Remember, think of your unit circle. Since you're talking about cosine, it's the x coordinate. So when you're looking at 0 radians, what's your x coordinate? Good, it's 1. But then you got to do 1 times 3, which is 3. Look at pi over 2. Remember, that's up here, right? On the circle, that's up here. And you're looking at the x-coordinate. So at pi over 2, the cosine of it would be, good, 0. And 0 times 3 is 0. And then we're moving to pi. Remember, that's over here on the circle, right? On the unit circle, that's over here. And since you're talking cosine, you're talking about the x-coordinate, which is -1. But then you've got to multiply it by 3, don't you? Which gives you, -3. Okay. At 3 pi over 2, remember that's the one down here. So the cosine of that is, excellent, it's 0. And 0 times 3, 0. And then we complete the circle back to 2 pi, which is over here. What's that x-coordinate? Because you're talking cosine. What's the x-coordinate? Yeah, the x-coordinate is 1 times 3 is 3. So, I'm going to connect my dots, and my question to you is this. Did I get the same shape that I got when I graphed the parent graph? Yeah, it's still the shape of a valley. And it's just going to be the shape of a valley all the way to positive infinity and all the way to negative infinity. With me? Is the range still -1 to +1? Nope. Do you see what happened? This 3 in front, since this affected the y values, it also affected the range. So here's the deal. The amplitude is going to dictate the range. And based upon the amplitude of 3, my range went from a -3 to a +3. Amplitude is always positive. It will always tell me my range, which goes from -3 to +3 in this case, because there's a 3 in front. When we did the parent graph, it was just cosine of x, wasn't it? What was the number in front? Yeah, the number in front of the parent graph was a 1. Notice my range went from -1 to +1, didn't it? Does this make sense? Okay, so hang in there. We're going to graph. Okay, so we have a new trig function to graph. Y equals -1/2 sine of x. How do I start graphing it? I start by asking myself, what's the amplitude? Your amplitude in this case would be what? Remember what I mentioned a few minutes ago. Amplitude is always what kind of SIGN, sine. That's right, it's always positive. So my amplitude is a +1/2. The amplitude always dictates the range. So in this case, my range should be what? That's right, the range should be a -1/2 to a +1/2. Right? Remember, the next question to ask yourself is, does it flip? And the way you tell if it flips is, yeah, there's a negative sign in front, which means the answer is yes, it flips. So remember the sine graph. What's the shape of a sine graph? It's the mountain to the valley. But if it flips, that's right, it's going to be the valley to the mountain, isn't it? So I should get the shape looking like this, shouldn't I? Okay, so let's see if we do. Nothing added or subtracted to the x, which means there's no left or right shift going on, correct? So I'm still going to start at 0 radians. 4 quadrants of the circle, 4 intervals that I'm going to work with, because that gives me my shape. Everything else is just like a rubber stamp. You just keep stamping it left and right. We're still going to be at pi over 2 for the second tick mark. The next tick mark is at pi. And then 3 pi over 2, and then back to 2 pi. Are you with me? And according to what you've told me, since the amplitude is 1/2, my range should go from a -1/2 to a +1/2, right? And the graph should flip over, shouldn't it? Well, let's take a look. So, I'm going to plug in 0. And I'm dealing with the sine graph, right? So, you got to remember, that's over here on the unit circle. and the 0 radians, remember the point at 0 radians. So sine is the y coordinate. So what's the sine at 0 radians? Good, 0 times a negative 1/2, still 0. Got it? Okay. Now I'm looking at pi over 2, which was up here on our circle, right? Remember the coordinates up here. Sine is the y coordinate. So what's the y coordinate? Good, that's a 1. So the sine at pi over 2 is 1. So you're going to take 1 and multiply it by a negative 1/2, aren't you? Which will give you a negative 1/2. At pi, which is over here, remember the coordinate, remember the point there. Sine is the y, so the sine at pi is, good, 0 times a negative 1/2, still 0. At 3 pi over 2, that's down here, so remember the point down here. Sine is the y coordinate, so what's the y coordinate at 3 pi over 2? Good, that's a negative 1, but you're going to multiply it by a negative 1/2, which gives you a positive 1/2. Agreed? Complete the circle, go back to 2 pi. Yeah, that was 0, and 0 times a negative 1/2 is still 0. Okay, so when I connect my dots, I got exactly what I said I would get. We got the graph flipped over. We got the valley to the mountain since we flipped over sine. Does this make sense? The domain is still negative infinity to positive infinity, because remember, this shape is what we're going to get no matter how many rotations in the positive direction we go or the negative direction. This is the shape for this particular function. Got it? Okay, so hang in there. We're moving into the next characteristic. Okay, so the next characteristics to graphing a sine or a cosine function is what's called the period. What does that mean? It means what is the length of one revolution around the circle? What is the length of one revolution around the circle? Got it? What is the, in a typical circle, when I start at 0, the full angle rotation takes how much? Yeah, that's 2 pi. Are you with me? So the period deals with angle, one full angle of a circle. When I start and end, how long is that in radian measurement? Are you with me? So, period deals with the length in radians of one full rotation around the circle. I'll say it again because some of you are going to write that down. When you talk about the period, that is the length in radians of one full revolution around the circle. Cool? Okay, so let me give us an example so we have something to work with. So now, you're like, okay, so how do I start graphing that? Well, you've got to gather the information first. And the first piece of information you're going to gather is amplitude. We always start back at the very first characteristic we learned, amplitude. So in this particular case, your amplitude is, good, 2, because it's in front, right? The amplitude will dictate the range. So what's my range going to be? Yeah, inclusive, which means brackets, -2 to 2. Got it? After you ask yourself what the amplitude is, and hence the range, you're then going to ask yourself if this graph is going to flip. And will this graph flip? Good. Some of you said no. Why was it a no? Because in front of the 2 is no negative sign. So that's why it's not flipping. So since this is a cosine graph, what's the shape of cosine? Yeah, the shape of cosine is a valley, isn't it? So this graph is still going to maintain the shape of a valley. Remember that. Good? And now we have a new question to ask ourselves. And the new question to ask ourselves is the period. Well, here's how you're going to find the period. Remember what we mentioned. The period is, in radians, 1 full revolution around the circle. In a typical circle, 1 full revolution is how many radians? Good, 2 pi. So to find the period, I'm going to take 2 pi and I'm going to divide it by the coefficient of x, which is this b right here. Okay? The coefficient of your x is b. Well, in my example, that coefficient is, that coefficient is 4, which means the period is going to be equal to pi over 2. Got it? Okay, now, don't go anywhere yet. Hang in there a second. Don't start writing anything down that I'm going to write in this very moment. Yes, this 4 affected the x's. Remember your parabola. The only time it moved left and right is if you added or subtracted something to it on the inside of parentheses, correct? I didn't add anything to the x, I multiplied, so there's no left-right shifting. So we're still going to start at 0 radians. The circle still has how many quadrants? Excellent, 4 quadrants. Now here's the deal, okay? With these 4 quadrants, according to what you just found, 1 full rotation around the circle is going to be a length of pi over 2. Are you with me? 1 full rotation around the circle is now a length of pi over 2. So the length of 2 pi got shrunk to pi over 2. Do you think these angle measurements are going to remain the same if your circle shrunk? Nope, it's not. Which means, in addition to finding the period, you now need to find the length of each interval. I call it LOE for short. Why? Because I get tired of writing length of each interval. So I call it LOE for short. Now, here's how I'm going to get you to understand what the length of each interval is, or how to find it. In my typical circle, I have 4 quadrants, right? We start at 0 radians, we end at 2 pi. 2 pi is the length in radians of 1 full circle. If I take 2 pi and divide it by the 4 quadrants, I get pi over 2, don't I? Isn't the length of each quadrant pi over 2? Good. Which means for us to find, in this case, the length of each of these quadrants, I'm going to take the pi over 2, which is the new full rotation amount, and I'm going to divide it by those 4 quadrants. And yes, I'm expecting you remember how to divide by fractions. So you're telling me the length of each interval is going to be pi over 8. You're telling me in this case each of these is now going to be pi over 8. Got it? Let me recap. Since a circle has 4 quadrants, the new length of 1 full rotation, around the circle, in this case was pi over 2. And you had to take pi over 2 and divide it into 4 quadrants, which told you each quadrant had a length of pi over 8. With me? Okay, so let's talk. So we start at 0 radians, agreed? And when we start at 0 radians, we are going a length of pi over 8, aren't we? So up here, would have a measurement of pi over 8. And then from pi over 8, we're going to go another length of pi over 8, aren't we? Do you agree? Because the length of each of these quadrants is now pi over 8, isn't it? So, I start at pi over 8. I'm going another pi over 8, which means you're going to, you're going to have to add these guys together, aren't you? That's going to give you 2 pi over 8, isn't it? But that reduces to what? Good. Pi over 4. So, this next one is pi over 4. And then you're going to go, the next quadrant has another length of, has the length of pi over 8, right? Because that's the length of each of these quadrants, that's the length of each of these intervals. So now I get to take the 2 pi over 8, and that's right, I'm going to have to add pi over 8 to get there, right? To get to the next mark. What will this be? Yeah, this will be 3 pi over 8, won't it? So, this next is 3 pi over 8. And then last but not least, you got another pi over 8 to add to 3 pi over 8, right? To this next, because this next quadrant has a length of pi over 8, and when you add it, what do you get? Yeah, you get 4 pi over 8. But 4 pi over 8, doesn't it reduce to pi over 2? Which is exactly where I should have ended up. From 0 to pi over 2 has a length of pi over 2. Cool? Okay. And my range is going from a -2 to a +2. Got it? Okay. So, remember, in this particular case, I started at 0. I had to add this length of pi over 8, which ended up at pi over 8. And to the new mark up here, the new radian up here of pi over 8, I had to add another pi over 8, which ended up at 2 pi over 8, etc. Good? This is how we get these new angle measurements, these new radian measurements. You shrink the circle, each quadrant is going to be smaller also. Good? Okay, so now, let's graph. I have y equals 2 cosine of 4x. So I'm just going to write it up here. Y equals 2 cosine of 4 times x. Well, so the first angle I'm going to plug in is 0. So what's 4 times 0? Yeah, that's 0. So I'm taking the cosine of 0, aren't I? All right, well, the cosine, and I'm just going to say this is 0, isn't it? The cosine of 0 is what? Yeah, it's 1. We already know that. So what's 1 times 2? 2. Okay, now I'm plugging in pi over 8. And when I plug in pi over 8, the first thing you're going to do is 4 times pi over 8, which is, pi over 2. Well, that's interesting. This changed to pi over 8, but I'm still taking the cosine of pi over 2. Okay, well, what's the cosine of pi over 2? Yeah, that's 0, isn't it? And 2 times 0? Yep, still 0. Okay, next one I'm plugging in is, that's right, pi over 4. Not pi, yep, pi over 4, sorry about that. So, let's plug in pi over 4. So, first thing is 4 times pi over 4, which is what? Pi. That's interesting. My third mark changed to pi over 4, but I still end up taking the cosine of pi. All right, good enough, because I know the cosine of pi. What's the cosine of pi? -1 times the 2. Yep, -2. All right. Maybe some of you guess what you're going to end up getting next when you plug in 3 pi over 8. Let's see if you do. So 3 pi over 8. Yeah, that's 12 pi over 8, which reduces to 3 pi over 2. I'm still taking the cosine of 3 pi over 2 on the fourth angle measurement. Good enough. Cosine of 3 pi over 2. Yep, that's 0, and 0 times 2 is 0. And last but not least, you are now plugging in, that's right, you are now plugging in pi over 2. And when you take pi over 2 and you multiply it by 4, yep, 4 pi over 2, which is back to 2 pi. So we ended at 2 pi once again, even though my last angle is pi over 2. Well, cosine at 2 pi, 1 times 2, 2. So, I was supposed to get the valley graph, and I got the valley graph. Do you notice, even though I plugged in these new angle measurements, I had 5 of them to plug in, even though I plugged in 4 really, different angle measurements, I still had to plug in the 0, a total of 5 angle measurements. I still ended up taking the cosine at 0, and then pi over 2, and then pi, and 3 pi over 2, and back to 2 pi. I still ended up taking the cosine of my typical angles around the circle. If we do things correctly, it will always turn out that way. Always. Again, if we do this correctly, we will always end up taking the cosine or sine of 0, pi over 2, pi, 3 pi over 2, and then back to 2 pi. Always. Okay, so hang in there. I got another example. Okay, so let's look at this particular trig function that they're asking us to graph. Y equals sine of pi over 2x. So, I need to gather the information first. What's the first piece of information we're going to gather? Good. We're going to gather the amplitude first. My amplitude in this case is what? It's a 1, because there is a 1 in front of here, isn't there? The 1 dictates the range, or I should say the amplitude dictates the range. So in this case, my range will start at, good, -1, end at +1, inclusive, which means brackets, correct? After we identify the amplitude with the range, good, you have to see if this thing is going to flip. Is this thing going to flip? Nope. So the sine graph is going to be the mountain to the valley because it's not flipping, right? Good. Next thing is the period. Now, what is the normal, in radians, what is the normal length of one full revolution around the circle? Good, 2 pi. So you're going to take 2 pi and you're going to divide it by the coefficient of x. So I am going to write it this way because sometimes it's easier for me to see it that way than as a complex fraction. So yes, of course, I'm expecting you remember how to divide fractions, which means it looks like I'm just going to get, what? 4 pi over pi, which means we just get 4. So it looks like the period is just 4. Like, wait, there's no pi there. Well, so there's no pi. That's okay. If the pi isn't supposed to stay, it doesn't have to stay. So don't assume it's supposed to. Got it? Okay. When you find the period, the length now, in radians, of one full rotation around the circle, what's the next thing you find? Good. You find Loe. So, the length of each interval. How do you find the length of each of those intervals now? How do you find the length of each of those quadrants? Now that the period has changed, now that the length in radians of one full revolution has changed, How do you find the length of each quadrant? I take the new radian measurement and I divide it by 4, don't I? Which in this case will give me 1. So the length of each of my new intervals, or my new quadrants, is a length of 1. Good? Okay, so let's see what the graph looks like. Still starting at 0. I still have 4 quadrants, which means I still have 4 intervals. And now the length of each interval is 1. So, remember, let me get my circle back here, because some of you may need to see it this way. I'm starting at 0, correct? And now, this interval has a length of 1. That quadrant has a length of 1. Good. So, when I add this, 0 plus the 1, what do we get? Yeah, we get a 1 here, which means this is 1. The length of this new quadrant, or this quadrant, the new length of this quadrant or interval is 1, because that's what you told me. So this 1, and I'm going to add it to this 1, gives me, yep, 2. So the second or the third interval mark is a 2, isn't it? Okay? Or I should say the third tick mark, because it's the end of the second interval. Okay, so you get the idea. You're going to add another 1 to this, which gives me 3. And then I have one more quadrant, which means one more interval. And so when I add these, I'm going to get 4. So the length from 0 to 4 is 4, isn't it? Good. And you told me my range was from a -1 to a +1. Cool? All right, so let's start working with this. Now, mind you, some of you might benefit from writing down, just like we did the last problem, writing down by plugging these numbers in. So the first number you plug in is 0, isn't it? Well, what's pi over 2 times 0? Yeah, 0. And now I'm taking the sine at 0 radians, which is how much? Good, that's 0. And then the next angle I'm plugging in is, yeah, the next angle we're plugging in is 1. So I have to do pi over 2 times 1, which is what? Pi over 2. No surprise, I'm back to pi over 2. So what's the sine of pi over 2? Good, 1. Okay, the next radian I'm plugging in is 2. What's pi over 2 times 2? Pi. I'm back at pi. Well, that's good, because I know the sine at pi. What is it? It's 0. With me? Getting the hang of it? Okay. Next I'm plugging in is the 3. So what's pi over 2 times 3? Yep, 3 pi over 2. And what's the sine at 3 pi over 2? Good. -1. And can you guess what happens when you plug in the 4? That's right, you're back at 2 pi, and you know the sine at 2 pi is 0. So I did get the mountain to the valley graph, didn't I? Cool? Okay, so hang in there. I got another characteristic.